In my last video, I have mentioned about direct sum of two subspaces. Now let us look at direct sum of n subspaces. Suppose I have a vector space V over a field F, and I have n subspaces of V, say V1, V2, V3, like that. N subspaces of V. Then I'm calling V as a direct sum of these subspaces if every vector in V can be uniquely expressed as V1 plus V2, like that, Vn, such that where each Vi belongs to the subspace Vi. Okay. V is a vector space over the field F, and V1, V2, V3, Vn are the subspaces of V. Then we call V as a direct sum of these subspaces if every vector in this vector space can be uniquely expressed like this, and we denote this direct sum as V equal to V1 direct sum with V2, like that, Vn. Okay, for example, suppose I have a vector space Rn, and that is nothing but the Euclidean space. Say suppose Vi, each Vi is a vector which is an n tuple x1, x2, like that, xn, such that xj is equal to 0 whenever I is not equal to j. Okay. Suppose the subspace Vi is like this. Vector space is Euclidean space, and Vi is a vector which is an tuple. In that, entries are equal to 0 if I is not equal to j. If I equal to 0, if I equal to j, then entries will be equal to x1 or x2, like that. Okay. Then so any vector can be written like this. This vector here is nothing but x1, x2, x3, like that, xn, right? And this can be rewritten as x1, 0, 0, dash dash 0 plus 0, x2, 0, dash dash 0, like that, 0, 0, dash dash nth element, xn. Every vector can be written like this. See, when I take n tuple, addition means I'm adding the first coordinate, first one, everyone. So I'm getting x1. Then I'm adding with the second one. See, I is not equal to j. Here I is not equal to j. Therefore, these entries are zeros. When I equal to j, x is only x1. Okay, like that. So this can be the example for direct sum of vector space V with the subspace Vi, which is defined like this. Now let us look at few problems on this subspace generated by a subset. First problem is, let V1, V2 be the subspaces of V. To show that V1 plus V2 is a subspace generated by V1 union V2. So when it is asked to show that it is a subspace generated by something, I have to show that this V1 union V2 is contained in this, and I have to show this is the smallest subspace containing V1 union V2, so that I can say that this is generated by this. Okay, so first thing I have to show this is contained in this. For that, see, I know V1 is contained in V1 plus V2 because these two are the subspaces. Similarly, I can write V2 is contained in V1 plus V2. So from these two I can write V1 union V2 is contained in V1 plus V2. Okay, so first thing is over. Then I have to show that V1 plus V2 is the smallest subspace containing this. So let me assume that suppose there is one subspace which is containing this V1 union V2. Suppose if W is a subspace containing V1 union V2. V1 union V2. Then I know I can write V1 is contained in W. It's a subspace containing this union, so V1 is contained in W. Similarly, V2 is contained in W. Therefore, I can say V1 plus V2 is also contained in W, which implies that V1 plus V2 is the smallest subspace containing this, because V1 plus V2 itself is contained in W and W is a subspace containing this. So I can say this is containing this. So I can say this is the smallest subspace. Therefore I can say V1 plus V2 is the smallest subspace containing V1 union V2. Hence I can say V1 plus V2 is generated by V1 union V2. Second problem is find the subspace generated by the vectors 1, 0, 0 and 0, 2, 0 in R3. So what I have to do, I have solved one such problem. I have to take two elements from scalars from the field F and I have to check for the vector addition along with the scalar multiplication. Suppose I consider this V1 as 1, 0, 0 and vector V2 is 0, 2, 0. I have to check for the scalars, say alpha, beta from the field F. Let me take alpha V1 plus beta V2. So this will be alpha into 1, 0, 0 plus beta into 0, 2, 0, which will be alpha, 0, 0 plus 0, 2 beta, 0, which is nothing but alpha 2 beta, 0. In the sense, here I am getting z coordinate as 0. In the sense, x, y values are there, z coordinate is there, but the value of the z coordinate is 0. Therefore, I can say the subspace generated by this is xy plane. It's a plane, okay? Z coordinate is 0. So answer is xy plane. Third problem is find all the subspaces of R3. R3 is a vector space. Therefore, R3 itself is one subspace. Okay, and one more I can say, that is 0 element subspace formed by this, that is nothing but 0 subspace. Okay, and R3 means x, y, z coordinates will be there. Therefore, it's a plane, I can say. Therefore, all the planes passing through origin is a subspace. Plane passes through the origin this is also a subspace. In fact, it is denoted by the equation, say, for some a, b, c, for some numbers a, b, c, I can say ax plus by plus cz equal to 0. It's a plane passing through the origin, and of course I can take the line, all the lines passes through the origin. These are the subspaces formed by R3. Fourth problem is, suppose I have two subsets S and S dash of a vector space V. Then I have to show that S is contained in S dash. Suppose S is a subset of S dash, then L of S is a subset of L of S dash. And I have to show this result. The first one is, it's a trivial, it's easy. In fact, since we know that S is a subset of S dash, it clearly implies linear span of this is a subset of linear span of this, because this is contained in this. Okay, this one I'm not writing, I'll just write the proof for this. Okay, I have to show this is nothing but sum of L of S plus L of S dash. I know S is a subset of S union S dash. Okay, so I can write from this result itself, L of S is contained in L of S union S dash. Okay, similarly I can write S dash is contained in S union with S dash. Therefore I can write L of S dash is contained in L of S union S dash. Now I'll take up these two results. I'll write L of S plus L of S dash is contained in L of S union S dash. Okay, this is the first part. Now if I take any vector in L of S union S dash, which is a linear span of S union with S dash. How is that? Since it's a linear span, which is a linear combination of vectors. So I can write this vector V as, say, summation AI Vi, I ranging from 1 to n, say, and each vector Vi belongs to this S union S dash. Now this can be rewritten as, say, summation AI Vi, where this Vi belongs to S only. Okay, and I'll write something extra, AI Vi. I'm splitting this such that few Vi's are in S and few Vi's are in S dash, so that Vi is in S dash. I'm splitting this linear combination such a way that now this is L of S. Okay, so this is contained in L of S plus L of S dash. Okay, therefore I can say, see, I have proved this L of S plus L of S dash is contained in this, and if I take any vector, then that is nothing but that can be splitted in this way. Therefore I can write L of S union S dash is equal to L of S plus L of S dash. Now let us look at few definitions. First one is generating set. Suppose I have a vector space V over the field F, and S is any subset of the vector space V, then I'm calling S as a generating set for this V if the linear span of this S is nothing but vector space itself. Then I can say that S is a generating set for the vector space V. Next is linear dependency and linear independency of the vectors. suppose V is a vector space. I have set of vectors, say V1, V2 like that, Vm are the elements of V. Then I'm calling this set as linearly independent set if A1 V1 plus A2 V2 like that, AM Vm is equal to 0 for any AI belongs to F, then AI equal to 0 for all I. Then I can say this set of vectors as linearly independent. A set V1, V2 dash dash Vm are the elements of V is said to be linearly independent set if whenever this equal to 0 implies all AI equal to 0, then I can say that this is a linearly independent set of vectors. If not all AIs are equal to 0, means there are some scalars which are not equal to 0, then I am calling the set of vectors as linearly dependent. So this is same as writing the elements or the vectors V1, V2 dash dash Vm are linearly dependent if and only if there exists say A1 V1 dash dash AM Vm equal to 0 with some AIs not equal to 0, then I can say that the vectors are linearly dependent. Okay, it's a non-trivial relation in fact. Non-trivial relation between this is equal to 0 with some AI not equal to 0. Then I am saying this set of vectors as linearly dependent. So let us look at few vectors and I will check whether they are linearly independent or not. The first set of vectors I am considering, say the vectors are 1, 1, 1, 2, 2, 0 and 3, 0, 0. I have to check whether these vectors are linearly independent or not. So let us name the vectors. I'll take this as V1, V2 and V3. Okay, first I have to look at the vectors. If one can be written in terms of others, linear combination of others, then I can directly say that they are linearly dependent. Okay, or else I can use the definition of linearly independent vectors. If this A1 V1 plus A2 V2 A3 V3 equal to 0 vector in fact, if I am getting all AIs equal to 0, then these are linearly independent. Okay, let us look at it. A1 1, 1, 1 plus A2 into 2, plus A3 into which is equal to 0 vector. I am equating it like this. Okay, now this whole thing I am getting, if all AI is equal to 0, then these vectors are linearly independent. So this I'll multiply A1 1 A1 A1 plus 2A2 2A2 0 plus 3A3 0 0 which is equal to 0, 0, 0. So I'll take up this with this. So A1 plus 2A2 first coordinates from everywhere, 3A3 which should be equal to 0. Similarly A1 plus 2A2 equal to 0, a1 plus 0 equal to 0. Now I got a1 equal to 0. I'll substitute this a1 equal to 0 in the second equation. What happens? 2a2 equal to 0. So a2 equal to 0. If I put a1 equal to 0, a2 equal to 0 in the first equation, then a1 is 0, a2 is 0, plus 3a3 equal to 0. So that I am getting a3 equal to 0. Therefore, I got all ai's equal to 0. Therefore, I can say v1, v2, v3 are linearly independent. These are my vectors 1, 3, 2, 1, minus 7, minus 8, 2, 1, minus 1. I have to check for the linear independency or linear dependency. Okay, to check whether they are linearly independent or not. So I am applying a1 v1 plus a2 v2 plus a3 v3 equal to 0 vector, and I am getting these three equations. So in the previous case, I directly got one variable equal to 0. I mean one constant equal to 0. It's a scalar always. So here in this case, I'm not getting like that. So I have to combine the equations. So let me name the equations. I have to get the values for the a1, a2, a3. So if I take these two, 2 and 3, if I add these two, if I add equation 2 with the equation 3, I am getting 5a1 minus 15a2, which is equal to 0. So that I am getting a1 equal to 3a2. Okay, and if I apply this a1 equal to 3a2 in the equation 1, if I apply this in equation 1, the equation 1 will be 3a2 plus a2 plus 2a3 will be equal to 0, which is nothing but 4a2 equal to minus 2a3, in the sense a3 equal to minus 2a2. So 1 can be written in terms of others. So in this situation, I am just trying with the trial and error method. Let me give some values to a1, a2, a3 like that, and we'll check. Okay. Suppose if I give a value for a1, suppose if a1 is equal to 3, then what happens to a2? If a1 is 3, then a2 is 1, because 3 equal to 3a2, so a2 will be 3 by 3, which is equal to 1. And a2 is 1 in the sense a3 is minus 2. So that you can check all these ai's are not equal to 0. Therefore, I can say these vectors are linearly dependent, in the sense they give you a1 v1 plus a2 v2 a3 v3 equal to 0 0 comma 0, but these ai's are not equal to 0, in the sense, see, this a1 is 3, I have taken 3 into the first vector, and a2 I got 1 minus 7 minus 8, and a3 is minus 2, 1 minus 1. This is giving me 0 vector, but ai's are not equal to 0. Therefore, I can say v1, v2, v3 are linearly dependent. This is one method of checking, and there is one more method, in fact 2 more method. If you are getting 3 equations with the 3 unknowns, okay, then checking for linear dependency is by using the determinant of a matrix. You are writing the coefficients in terms of matrices, and you are checking for the determinant. If the determinant is 0, if the determinant you are getting of the coefficient matrix. Okay, if determinant becomes 0, then I'm saying that the vectors are linearly dependent. If the determinant is not equal to 0, then the vectors are linearly independent. Okay, and this is only for the square matrix, in the sense you are getting number of equations and number of unknowns are equal. In that case, you can write the equations, linear system of equations, in terms of square matrix, which is a coefficient matrix, and you can check for the determinant. This is easy when you have only 3 equations, or 2 equations with 2 unknowns, or 3 equations with 3 unknowns. More than that, it is quite difficult. And of course, if you are not getting a square matrix, then you have to check. This is only for square matrix. Okay, if it is not a square matrix, then rank equal to number of vectors, then I can say the vectors are linearly independent. This is for non-square matrix. Okay, otherwise they are linearly dependent. This is one method. Say I'll take up one example for this. No, I'll do the same example. This one, if I take, these are the 3 equations you are getting. Here I have got already 0, but I'll take some other example. So suppose you have these vectors and I have to check for the linear independence nature. Okay, for that I have to write these vectors in terms of matrix, and I have to find the determinant. If the determinant is not equal to 0, then it is linearly independent. Okay, first row is 1 2 1 2 1 0 1 minus 1 2. So I'll expand the determinant. So which is not equal to 0, therefore I can say V1, V2, V3 are linearly independent. Okay, this is another method for checking the vectors, whether they are linearly independent or not. Another way is, so I'll explain it with the example. Suppose I have a vector space R3 over R. Okay, I have 2 set of vectors. Say this S1 is 1, 2, 3. And another vector is -3, -6, -9, suppose. And another set is this 1, 0, 0 and 0, 0, 1. I've mentioned this how to check, in fact. How? Because you have to check whether one vector can be written as linear combination of the other vectors. If you have 3 vectors, then it is quite difficult. But if you have only 2 vectors, then you can just look at the numbers over here, right? This, if I multiply with some value, I'm going to get this. Or this can be written as some number into this. You can check it. So in case of S1, the set S1, this -3, -6, -9 can be written as some number into 1, 2, 3. In fact, that number is nothing but -3, right? -3 into 1 is -3, -3 into 2 is -6, -3 into 3 is -9. In fact, the vector V2 can be written as alpha into V1. So one vector can be written in terms of other, in the sense this set has to be, these vectors are linearly dependent and this set is linearly dependent. Okay. vectors this or set S1 is linearly dependent set. And in case of S2, see here you cannot write it like this. Whatever you multiply to this, you are not going to get this. Whatever multiply to this, you are not going to get this. Therefore, you can directly say that set S2 is linearly independent, or else you can just take the scalars and multiply with the vectors. Okay, then check for this value of this scalars. Here you are getting alpha 1 equal to 0 and alpha 2 equal to 0. Therefore, these vectors are linearly independent. Okay, if you have only two vectors, then it is quite easy.